The theme is applications of integrable systems. Our first keynote speech will be uh, Associate Professor Jon Links um, on the quantum turntable.
Thanks, Anthony, and thanks to the organisers for offering me this opportunity to speak today. So I'm going to describe to you this construction for a quantum turntable, which is based on the mathematical principles of integrability. We'll get to exactly what a quantum turntable means later on. We'll just start off with an overview of the situation. So, as you all know, the theory of quantum physics offers up a lot of strange phenomena that, when they were first proposed, ran contrary to what we expect our physics, the laws of physics, to do from our personal experience. So, there's several examples of this. One is quantum tunneling. So, in the quantum framework of physics, particles can tunnel through barriers where they wouldn't have the energy to do so in a corresponding classical system. We've got things like state superposition. So this is popularized famously through the concept of Schrodinger's cat, where the cat is in a superposition state of being dead and alive. And we've also got the property of entanglement, which Einstein referred to as spooky action at a distance. So these are some of the examples that we come across in the quantum theory, which are hard to kind of imagine, at least first time you come across them, because they sort of don't correspond to what we perceive in our classical view of physics. So for a few decades now, there's been a lot of effort to try and use these properties of quantum physics to develop technologies which give an advantage over the corresponding classical approaches. So some famous examples of this are there's Shor's factoring algorithm and Grover's search algorithm in quantum computing, which basically utilize these types of properties, state superposition and entanglement, to gain that advantage. So what I want to propose today is that when we study integrable and exactly solved models, that these can guide us into designing systems which might be able to exploit such quantum phenomena for our benefit. Okay, so to start things off, I'm going to introduce this boson tunneling model. It's a fairly simple model. So here's a schematic representation of it. So we've got a double well potential. So here's our potential, and we've got a system of bosons. So these are indistinguishable particles, and basically imagine this to be a very low temperature, nano Kelvin scale. We've got the particles can occupy either one of the wells of the system. So we can have particles in the one on the left, let's call that site 1, and particles in the well on the right, we'll call that site 2. And then these particles interact among themselves. So that's going to be parameterized by this value K. And so, for example, if K is positive, there's an energy cost each time you put a particle into a well, because the particles want to repel each other. We have this tilt mu that appears here. So that's just saying that there's an offset between the two minima of the potential. And then this is a tunneling model. So the particles can tunnel from the left to right and vice versa. And there's a coupling parameter epsilon associated with that. So in a classical system, if the particles were just sort of occupying here, they wouldn't be able to get over this bump in the middle to get to the other side. But in the quantum description, they can tunnel between the two wells. Okay, so that's the sort of setup. So we want to write down a Hamiltonian that describes this system. So here's the Hamiltonian for the system. So basically, we've got boson creation and annihilation operators satisfying the usual commutation relations. Very familiar with commutation relations. And we have the number operators. So basically, we have two types of boson indices 1 and 2 associated with the two minima of that potential. So they can either occupy site 1 on the left or site 2 on the right. So we have number operators given by these expressions here. Nj is equal to Bj dagger times Bj. And then the three sort of components that go into the interactions for the Hamiltonian are the interactions given by this expression here. First of all, with the coupling K over 8, that's just conventional, put that factor of 8 there, doesn't really mean anything. But this first term here, you see that this is n1 minus n2 squared. So if we want to minimize that expression there, because it's a square, we minimize it by setting n1 equal to n2. So classically, we can think of the K measuring the repulsion between the bosons. So the energy is minimized just with respect to that particular term there, if we put half of them in site 1 and half of them in site 2. And then every time you move one from one site to the other, then there's going to be non-zero, and there's an energy cost associated with that. The second term here, this is just encoding the tilt. So you've got coupling mu over 2, and then it's just related to the difference between the particle numbers between the two sites. So again, if you take a particle in site 1 and then move it over to site 2, you're going to get an energy cost of mu. So to associate with that process. And then we've got the last term here. This is the tunneling term. So that says that a particle at site 2 can be destroyed and tunnel across and get created in site 1. And then we have the process in the other direction. All right, so they're the terms in the Hamiltonian. So I want to start with this rather simple model and see how we can treat this mathematically in terms of obtaining what we call an exact solution for it. So there's a few symmetries involved in this Hamiltonian, which I should mention. First one is that the sign of the epsilon is not important. You can change that by unitary transformation. So in other words, the energies of this Hamiltonian will be even functions of epsilon. The sign of mu is equivalent to just flipping, like reflecting the potential. So if you change the sign of mu, that's equivalent to a reflection, which is equivalent to just interchanging the labels 1 and 2. And the other thing to mention is that this quantity here, the total number operator n, which is n1 plus n2, that commutes with the Hamiltonian. So that's a conserved quantity. So you can see that number operators commute amongst themselves. So n being equal to n1 plus n2 will commute with this term and with this term here. And with regards to the last term, you see that particles are neither created or destroyed overall. They simply move between sites 1 and 2. So the total number of them, n1 plus n2, is conserved. And that's easily confirmed by calculating the commutator of the Hamiltonian with the number operator. You can show that's equal to 0. So what we've got here is a system with just 2 degrees of freedom. The 2 degrees of freedom are basically associated with the 2 copies of the boson algebra. And we've got 2 conserved quantities, the Hamiltonian itself and the number operator. So in the sense that the number of degrees of freedom matches the number of conserved operators, we have an integrable system. So it's very simple integrable system. Okay, so there's the Hamiltonian written again. So now I want to explain how we can get an exact solution for this system and what we mean by an exact solution. So basically, to get an exact solution for the system, we want to encode expressions for the energy spectrum and the eigenstates through some auxiliary equations. Okay, so this is a linear operator acting on these types of states here, these JK states, okay, which are just simply what we call Fock states. There's J particles of type 1 and K particles of type 2. And so if you take the span of all of these states, that gives us the Hilbert space for the system. So it's an infinite dimensional Hilbert space. But because the system conserves the particle number, we can actually work in a block diagonal form. So even though we've got an infinite dimensional Hilbert space, we can write it as a block where the first block would just be the vacuum. This is the vacuum state here where there's no particles. Then we'd have the sector with one particle states. So there'd be two of those, just the B1 dagger acting on the vacuum and the B2 dagger acting on the vacuum. And so on. We've got two particle states, three particle states. So we can work in this block form. So we take n to be fixed, the number of particles, and consider an eigenstate of the Hamiltonian. So we're looking at the eigenvalue equation here. H acting on psi is equal to E times psi. And we look for psi to be of this form here. It's just saying it's a linear combination of the basis states that have total particle number equal to n. I should say, if there's any questions at any point, please jump in and ask questions if something's not clear. Okay, so any state which is an eigenstate will be a linear combination of these basis states. Coefficients are denoted here by the alpha j. And then what we do is we just take this Hamiltonian and act it on this state here, and we get this expression here. So using the fact that the number operator is defined to be bk dagger bk, and if you reverse the order of those operators, bk times bk dagger, that's just the number operator plus an identity. So when you act these terms here, when you have the B2 acting on one of these states, you're going to get these expressions here for the nk plus I. And I should mention here, I haven't normalized the states here. For this calculation, it's not important to not have that normalization in place. It actually makes the equations cleaner if you don't have the normalization constants, which would be square roots of factorials appearing in the expressions. So we just take the expression for the Hamiltonian, apply it to this state here, and we get this expression here. So coming from the first two terms, n1 minus n2 acting on a state like this will just give us the n minus 2j squared, and then we get here an n minus 2j coming from this term. And then from the last term here, you see, because we've got these creation annihilation pairs, then they're changing the quantum numbers in the Fock states here. So when we destroy one in site one, we create it in site two. And then from this expression here, we get a coefficient j. And then likewise for the other process, we create one in site one and destroy it in site two. And then the coefficient is n minus j. Okay, so that's our expression for the Hamiltonian acting on an arbitrary state, written in terms of this expansion here. And so to force that to be an eigenstate of the system, then what we need to do is to satisfy this set of recursion relations here. So just going back to the previous page, you just write out put in for the psi on the left-hand side here, and then just match up the coefficients left and right. And then that gives us this set of equations here. Okay, so it's a three-term recursion relation. Okay, so let's think about the solution for this system of equations. So if we choose alpha naught to be equal to 1, so that's just fixing the norm of the state. We plug that in here, then that's going to determine alpha 1. So fixing alpha naught in here determines alpha 1. And then once we know alpha naught and alpha 1, we can stick that into this equation here and determine alpha 2. And likewise, we can keep going through and find these expressions for all the alphas. Now, you notice here that if alpha naught is equal to 1, then the expression for alpha 1 is going to be a linear function of the E. And then when you stick that into the next expression, the next line here, to calculate your alpha 2, then you're going to get E times the expression for the alpha 1. So that's going to be a quadratic function. So generally speaking, each alpha j is a polynomial in E of order j. And then when you impose this last term here, the boundary condition, if you like, then that gives us a polynomial equation of order n plus 1. Okay, so just going through the iteration of these recursion relations, in the final step here, we get a polynomial equation in E of order n plus 1. So the roots of that polynomial give us the energy eigenvalues. And I should have mentioned on the previous page here that the basis states here run from j equals 0 up to n. So for each value of fixed n, the Hilbert space has dimension n plus 1. So to get a complete set of eigenstates, we need to find n plus 1 energy eigenvalues, and that's what the polynomial that we get through applying this recursion relation is providing, those n plus 1 roots. Now, once we've got for the values of the roots, then we can plug these back in to find out what the actual values are for the alphas. Okay, so for each root, once I've solved the polynomial of order n plus 1, and I take a particular root and I plug it in to the first equation, then that tells me what the value is for alpha 1, and then take the alpha naught is equal to 1 and that value for alpha 1 and plug it in here, then that tells me what alpha 2 is, etc. So for each root of the polynomial, then this system of equations then in turn determines all the alphas. And from that, we can see that the spectrum of the Hamiltonian is free of multiplicities, because given a value of E, there's only a unique set of alphas which correspond to that. So there's no multiplicities in the spectrum of the Hamiltonian coming from that analysis. And we can take it a step further. What we can also do is transform this into a differential equation. So if we take those alphas now and then use those as the coefficients of some polynomial, we'll call that Q, then the recursion relation that we have on the previous page is exactly the same recursion relation you get from solving this eigenvalue equation in terms of these differential operators acting on Q. So we have a second order differential equation, and we're looking for polynomial solutions of if you think of the left-hand side as being a differential operator, then we're looking for polynomial solutions such that when you apply that differential operator to polynomial Q, then you obtain back Q with some eigenvalue E, which is the same eigenvalues as in the previous example. So the recursion relations can be used to describe the tunneling model, but can also be used to describe this differential equation. So they're mathematically equivalent. But the advantage of working with this differential equation, or looking at things through the lens of this differential equation, is that we can take this expression here for the polynomial, and rather than write it in terms of the powers of u, we can write it in a factorized form. So each polynomial can be factorized with roots given by complex numbers, and then I've got some proportionality constant here because I've chosen my alpha naught to be equal to 0. Sorry, alpha naught to be equal to 1. So there'll be some coefficient here, but this is a linear equation, so that coefficient is of no consequence. It just cancels out when you stick it into the differential equation that's above. So now if you look at this differential equation and you say, okay, think of Q as being in this factorized form. When you set U to be equal to one of the roots of the polynomial, then this term here will vanish and this term here will vanish because it's a root of the polynomial. So the root of the polynomial means that the value of the polynomial is 0 there. So then you've just got this term evaluated at a particular Vj plus this term here. So only terms involving the second derivative and the first derivative. And so if you rearrange those, divide through by the Q prime, you get the ratio of the Q double prime over Q prime evaluated at a root Vn is just going to be equal to minus this coefficient here divided by this coefficient here, which gives us this expression on the right-hand side. Oh. However, back here. Sorry about that. Alternatively, if you just use the definition for the polynomial Q, and you can show that the ratio of Q double prime over Q prime evaluated one of the roots is given by this expression here. So this gives us a system of equations that the roots of the polynomial must obey. And we can see from this form here that the roots of the polynomial for each eigenvalue E must be free of multiplicities. If there were multiplicities, then this term here on the left, it'd have a singularity with the difference of the roots here. But we can show that this can't occur from the differential equation itself. So, for example, if you think of a case where you suppose you have a root of multiplicity 2. Okay, so if you evaluate the polynomial q at that root of multiplicity 2, then q of vk will be equal to 0. So these two terms here will vanish, but also the first derivative will be 0 if there's a multiplicity of 2. So you've got this term as being equal to 0, and then you're just left with k times, let's say it's Vn, k times Vn squared over 2 times q double primed evaluated at Vn must be equal to 0. All the other terms go to 0. And then, because it's a root of multiplicity 2, the second derivative is non-zero, so that tells you that the root must occur at 0. But if you have a root occurring at 0, then that tells you that the alpha naught is 0. And then through these recursion relations, that tells you that the whole polynomial is 0. So that situation can't arise. So yeah, there's no multiplicities in these roots here. And we've got this nice system of equations that encode the behavior of the roots associated with each energy. So what we can do now is turn this around. In the previous example where I talked about the recursion relation, basically said you use the recursion relation to generate a polynomial in E of degree n plus 1 through equation 1, and then once you find the roots of that polynomial, you substitute back in to determine the alphas. But here,
Hi, John.
yes,
Sorry.
Anthony.
What happens if you had a higher order multiplicity? Like, I thought there
Yes,
was.
good question. I should have mentioned that. So if you have a higher order multiplicity, what you do is you take the differential equation and then you differentiate it such that the highest order derivative here will be non-zero, but all the lower order derivatives will be 0. And then you get to the same conclusion. So you just take the equation and differentiate it. Does that clear that up?
Yeah, thank you.
So yeah, so now I've got these equations that describe the roots of the polynomials. And if we go back to the differential equation written here, then what we can do is take the leading term expansion. So the q here is a polynomial of degree n. So if you look at this equation here, the highest order term will be u to the n plus 1. So that will occur from the leading order term with this q here times this term. There'll be a term of order u to the n plus 1. And also from the first derivative here times the u squared. But those two terms automatically cancel. Okay, when you take the derivative here, you get an n u to the n minus 1. So that will be an n times the epsilon u to the n plus 1 over 2. And that cancels that term there exactly. So then you look at the terms of order n, and you match those up. So you get one coming from the right-hand side here. So that's the E that appears there. And you look at all the terms on the left-hand side, and it's given by this expression here. So by matching the terms of order n, we get this expression for the energy, which is just a couple of constants plus the sum of the roots. So these VKs, these are the roots of the polynomial, and they satisfy these equations we had on the previous page. So this is an example of an exact solution for this, well, it's the exact solution to the original boson tunneling model they introduced. It's to say that you take this system of equations here, coupled nonlinear equations, and for each solution of those equations, you get a set of VJs. You stick the values of those into this expression here, and this gives you the energy. So these are called beta-ansatz equations, and this the combination of equations, the set of equations 3 with equation 2 is a beta-ansatz solution. And in this particular example, this has a nice property that we know that the V's are distinct, there's no multiplicities, and it's also complete. That all of the solutions can be attained through this particular set of equations here, the beta-ansatz equations and the corresponding energy expressions. Okay, so that's an example of an exact solution for a rather simple model where we've just got 2 degrees of freedom, just 2 bosons. Okay, so now I want to talk about something more general. So we move on to the next part of the talk. So now we're going to map that 2 degree of freedom model into one with 4 degrees of freedom. So as a first step, what we're going to do is something that's quite trivial, really. So the original model had 2 sets of boson operators, which had labels 1 and 2. The one that was labeled 2, I'm now going to label 4. Okay, so if you think of the terms in the original Hamiltonian, there was an n1 minus n2 squared terms with a coefficient k over 8. So I'm changing the coefficients now. So what was k over 8 before is now a u. And there was this tunneling term. It had a coefficient epsilon over 2. So I'm going to change the label 2 to 4. So that's my 2 tunneling terms there. Change the coefficient to this j over root 3. We'll see why I've chosen that particular combination shortly. And then there was another term that had the coefficient mu over 2 times the n1 minus n2. So now that becomes n1 minus n4 here. And I've changed that coefficient to be a j. And then I've introduced 2 more sets of boson operators, which got labels 2 and 3. So if you just, first of all, consider the original problem where I've just got things described in terms of the bosons with labels 1 and 4, then those terms, that term there, and that term there, they commute with things that have labels 2 and 3. So really, I've just taken the 2 boson system and I've just embedded it into a larger Hilbert space. And we can just choose these quantum numbers here, J2 and J3, to be arbitrary. And when you apply the number operators there, you get the eigenvalues. So basically, the number operators N2 and N3 are just acting as constants. Okay, when you apply the Hamiltonian, nothing happens to the labels J2 and J3. They're just acting as constants. So now for this 4 boson problem, I've got this Hamiltonian has 4 conserved operators. Okay, so the Hamiltonian itself is conserved. The total number operator in the original, sorry, let me just, sorry about that. The number operator in the original problem was n1 plus n2. Well, that now becomes n1 plus n4. That's conserved. Okay, so these tunneling terms here don't change the sum of n1 plus n4. So I've got the Hamiltonian, I've got n1 plus n4, I've got n3, and I've got n2. So they're my 4 conserved operators. So this is an integrable system. It's got 4 degrees of freedom. There's 4 bosons. And we've got 4 conserved operators. And so now what I can do is, because the N2 and N3 are conserved, they're basically just acting as constants, then I can just add in these particular combinations of them into the Hamiltonian. So I can take the N1 minus N4 and just multiply it by this term here. This is just a constant, N2 plus N3 squared. And here's the N1 plus N4, that's conserved. So putting in these extra constants doesn't change anything in terms of the integrability properties. So I've got this Hamiltonian here that will commute with N1 plus N4, N2, and N3. So this level here, it's kind of trivial. It's not really doing anything other than just sort of recasting it and changing some notation. But what's happened? Here we go. But you'll notice I've chosen these particular values for the coefficients, like I've put in here a j term in front of the n1 plus n4. So the reason I've done that is that now if you simplify it, you get this combination here. So the n1 minus n4 squared combined with the n2 plus n3 squared that appears here, and then the cross term that sits here, n2 plus n3 times n1 minus n4, that becomes that quantity all squared. And then the other terms give us this particular combination. Okay, so the next step is now to do a transformation. And then the transformation is obtained by applying a discrete Fourier transform. So we've got our system described in terms of these boson operators, which I've denoted by B's. And now I'm going to introduce some boson operators described in terms of these A operators, which related to the B's through these types of expressions here. So here, the new K, these are just roots of unity, third cube roots of unity. And you see that's why the root 3 that comes into the calculation that appears here has been put in there, so that'll cancel out when we substitute in. So now if I substitute in these B's into this expression here and write things in terms of the A's, we get this. So what I've done, I took a Hamiltonian with 2 degrees of freedom. I embedded it into a Hilbert space. So it effectively became a Hamiltonian with 4 degrees of freedom. But now I do a transformation which mixes up those degrees of freedom and gives me something non-trivial that's acting in the Hilbert space associated with the A operators. Okay, so now look at what we've got. We apply the transformation. Here I've put tildes on the ends because these are the ends associated with A operators, which are not the same as the ends associated with the B operators. Okay, the transformation doesn't preserve the structure of the number operators. So we get this first term here. It's U times this particular combination here, all squared, minus J times these tunneling terms. So if you look at the tunneling terms there, that's just saying that you can destroy a particle at site, an A-type particle at site K, and then it gets created at site J. And this is occurring for all values of J and K that are not equal. So we've got a 4-site model now where we've got tunneling from each site to every other site. And then we've got this type of interaction here, which doesn't look particularly physical. So we think of this sort of in terms of a picture. Well, this is one way we can represent it. So we've got 4 types of particles. So we have now 4 sites. The bosons can tunnel from each site to each other site. So that think of this as a graph, then each vertex of the graph has 3 edges to all of the other sites. And the one in the middle here, that's the one that's labeled 4. And so there's some type of interaction where this is sort of not isotropic. Okay, so somehow the site 4 is different from the sites 1, 2, and 3. Okay, so we need to now motivate, well, how can this be a physical model? Under what circumstances could we interpret this as some sort of physical model? So that takes me to the next slide, which is before I get to that, sorry, I need to say that because I've just done this transformation in terms of the discrete Fourier transform, the beta ansatz solution that I described earlier just transforms across. All I'm doing is a unitary transformation. So the expressions for the energies in terms of those beta ansatz equations just go through without any change, other than I've changed the notation. So if you just convert that to the notation in terms of the U and the J parameter, then this is the beta ansatz solution. So now here are the basis states in terms of the B operators for the sites 1, 2, and 3, and the A operator for site 4. Now I've got the normalization. You take that basis, you put it into here. I didn't talk about the eigenstates in the previous example because it's a bit complicated. I don't have time to do it, but I just want to mention here that we do have these expressions for the eigenstates. The eigenvalues are just the sums of the roots of the beta ansatz equations. So the structure here is the same, just the parameters have changed a little bit. And we've got these L and M quantum numbers associated to the B operators at sites 2 and 3. Okay, so L, M, and N are all conserved operators. That's lowercase l, lowercase m, and uppercase n, the total particle number, n1 plus m2 plus n3 plus n4. Okay, so that's the beta ansatz solution for the model. Right, so how do we turn this into a physical interpretation of the model? Well, the way that we can do that is by using appealing to dipolar interactions. Okay, so if you've got two electric charges, Q and Q prime, then I'm sure everyone is familiar with the form of the potential between those charges, which goes as 1 over R, and it's proportional to the product of the charges. Okay. A dipole occurs when you've got something which is overall neutral, but locally the charges have separated. So here's a representation of two dipoles interacting. So we've got a dipole at this position here, and then the charge, a positive charge and a negative charge are sort of separated. So we've got this vector A to describe the displacement. So you think of the point here as being like the sort of the center of charge, in analogy with center of mass. Then it's been displaced in the A direction for the positive charge and the negative A direction for the negative charge, and likewise here for the B. All right, so overall these are neutral. If you let A and B go to 0, then overall there's just no charge and there's no potential. But because you've separated them, now you've got potentials that are occurring between this positive charge and this positive charge. Okay, so they'll be repulsive. And this negative charge in this one, but also the negative with the positive here and the positive with the negative here. So if you use this formula for the electric charge and then compute the total potential for the dipole system, and then you just take the leading order terms with respect to the R, so you've got a 1 over R term here, then you get this formula for the dipole interaction. Okay, so the dipole interaction of this form here is significant because it's not a central force or a central potential. So the usual potential for electric charges, this is a central potential. It just depends on the distance. It doesn't depend on the orientation in any way. But when you have the dipole interaction, the orientation comes into play. So by the orientation, I mean the vectors A and B. As you change A and B, like you could, rotate these around, then the potential is going to change. So you see the potential depends on A and B in terms of these dot products, and also the dot product involving the vector, which describes the separation from the center of the charges. Okay, so that's a dipole interaction, and using that dipole interaction, we can actually give a meaning to the Hamiltonian that I had on the previous slide. Okay, so to kind of summarize what we've got here, we're looking at what's called an extended Bose-Hubbard model. So we've got three types of terms. We've got quadratic term involving number of operators with the same index, quadratic term involving number of operators with different indices, and then these tunneling terms, also called hopping terms. So if we think about our four-site system, rather than representing it in the plane, which is what I had on one of the previous slides, now think of this as being a dihedral structure in three-dimensional space. Sorry, tetrahedral structure in three-dimensional space, and assign dipoles to the sites, and then have all the dipoles, electric dipoles, pointing in the Z direction. Then you see that the dipole interaction between sites 1, 3, 1, 2, and 2, 3, they're all going to be the same because the dipoles are parallel, and also perpendicular to the the vector R, which is describing the separation between those sites. But the dipole interaction between site 4 and the other 3 sites is different because of the angle of the dipole is not perpendicular to this direction here. So that's how you introduce this sort of anisotropy, by dealing with this particular tetrahedral structure for the dipole interactions. Okay, so there's an obvious geometric symmetry here. So these terms here, these are what are accounting for the dipole interactions, these UJKs. So we can see that the interaction between site 4 and sites 1, 2, and 3, they're all equal, and the ones in the base of the triangle here are all equal. So it just comes from the symmetry of the problem. But to get back to the integral model that I had on the previous slide, then all I need to do is to set this parameter here, this U0, to be equal to these parameters here, the U1, 2. And we're going to call that 2U. So that's the integrable case that we had. And it turns out that this is more than just an integrable system. It's actually a superintegrable system. Okay, so going back to the transformation that we had here between the B's and the A's, if I go back to the Hamiltonian and write it in terms of the B operators, I get this expression here. I'm using a Q here rather than an N just because I'm reserving the N operator to be a number operator associated with the A boson operators. So just to make that distinction now, the ones associated with the B's I'm calling Q's. So this is a Hamiltonian that we have here. And the statement that this is an integrable system is just a statement that the Hamiltonian commutes with N and also commutes with Q2 and Q3, and these are all mutually commuting. But it turns out there's more commuting operators here. So if you take these B operators and do this Jordan-Schwinger type of mapping to SL2, or the angular momentum algebra, then you find that these J1 and J2 also commute with the Hamiltonian. So if I take this set here, H, total particle number, Q2 plus Q3, so that's the sum of number operators, and I take this J1 and J2, coming from these expressions here. So these are like think of it in terms of angular momentum algebra, this is the X and the Y, and that's the Z. Then this system here gives us, well, these 4 here all commute with the Hamiltonian. So we have a 4-site system, but we have 5 conserved quantities now. So this is something which is super integrable. And what that means is that we can now take the tetrahedron structure that we had here and rotate it. So when we rotate it, because we've got superintegrability, we can add this rotation term that appears here to this Hamiltonian. That's going to break one of the conserved operators, but we have 5, and it turns out it only breaks 1, so there's 4 remaining. So the rotational system is actually an integrable system. The static system is superintegrable, and we can rotate it and have an integrable system which is in rotation with our constant angular velocity. Okay, so this term in the Hamiltonian here, this is basically accounting for the angular momentum of the system that's contributes to the Hamiltonian through that rotation. All right, so okay, so that's what I've just described. We break the superintegrability by setting the system into rotation, but we still have an integrable system, and we have a beta ansatz solution. And what's really nice about this particular case is that when we set the model to rotate, so we've got this parameter zeta here that's associated with the rotation. Okay, that's the coefficient of this operator in the rotational Hamiltonian. That just enters this beta ansatz in this very simple way. The equations themselves don't change. We just get a contribution here to the energy. So we can now use this to describe the system. Okay, so if we take the Hamiltonian and we just pick a system of 6 particles, something that's quite simple, and plot the energy spectrum, then there are 84 energy levels. So here, this horizontal axis here, this is zeta divided by this constant xi, and here's the energy divided by xi. So these are dimensionless quantities here. This is measuring the angular frequency of the rotation. So we start at 0 here, and then we increase it. And this is the energy. So we've got ground state occurring here, and then we go up in to excited states. So we see here at 0 rotation, the energies form these bands. And then as we increase the system, those bands start to separate, and then all the energies here get mixed up. So what I want to do is zoom in on this region here with the circle. Okay, so when we zoom in on that, oops, that's the wrong way, this way. And just, yeah, zooming in on that particular band, there's 28 levels. And when we look at this particular value of the rotation here, then what we see is that all the energies become very ordered. We get these degeneracies, we get these crossings, and we get the spacing between these crossings being uniform. So here the dynamics of the system is going to become very simple. And what we do is we use what we call an effective Hamiltonian. So an effective Hamiltonian is basically saying when you've got a band structure like this, right here, there's 84 energy levels. So you're working in dimension 84 Hilbert space. But if you're just sort of focusing in this region here, you can basically throw away all of these lower energies and just keep these ones here. That's what we mean by an effective Hamiltonian. You sort of truncate the Hilbert space, and because all the states that have expectation values sitting around here will have predominant support on the eigenstates that appear in this band. So you can throw away everything down here and use an effective Hamiltonian. So when we plot here, we're actually using that effective Hamiltonian. We see this structure here. And then with the effective Hamiltonian, we can make some nice calculations about what's going on. So the effective Hamiltonian has a very simple sort of form in terms of the conserved operators, the Q2 and Q3. And this is the parameter xi that was introduced previously as this dimensionless parameter for the scaling. And then what we do is we can use this and we can compute these analytically, get these formulae for the number operator expectation values. Okay, so we focus on this case here where zeta is equal to xi on 3. That's the case that's corresponding here. Right? That's 1/3. So we look at that particular case and we use these number operator expectation values and just plot these and see what happens. So we start off with a system where we have all the particles starting in site 1, and then sites 2, 3, and 4 are empty. And when you plot those, you get these types of curves. So the first case here, this is without rotation. Without any rotation, you start off with all the particles in site 1, and the expectation values for site 2 and 3 are 0, and then you let the system evolve in time, and you see that particles will tunnel from site 1, so the expectation value decreases, and sites 2 and 3 by symmetry have the same expectation value. So they increase up until some point here, and then they start decreasing, and you get this periodic sort of behavior. But when you start with a rotating system, then it changes these expectation values. So this particular ratio, 1/3, then we find that the particles start in site 1 and they decrease down to 0. And here at site 2, starting at 0, they increase up to 1. Okay, so this is for a system of 19 particles. And from this second picture here, we get the notion of what we mean by quantum turntable. So I'm just going to show a video now. If this works. Okay, so this is what I mean by a quantum turntable for the system. So we're going to start the system. Okay, so we're starting with all the particles in site 1 here. This is just looking at the base of that tetrahedron, right? Basically, nothing happens at site 4. The particles just tunnel around between sites 1, 2, and 3. So we start off with all the systems in site one, and we're setting the system in rotation, and the particles start tunneling around. And what we find is they tunnel across to the other two sites, and then at a particular time, we find all the particles have gone from site one into site two, and we're at this point here. Then as it continues, all the particles that are in site two tunnel across to site three. Okay, so this is just a representation of the wave function, if you like. Just give an idea. So what's happening here is that the reason we call it a quantum turntable is we've got a system that's rotating, and the dynamics of the particle in the system are also rotating, but they're rotating at a different frequency from the physical rotation of the device. And that's why we refer to it as a quantum turntable. Okay, so just one more time. So that's just for a very simple initial state where you start off with all the particles at one site. All right. So go back to the slides now. Okay, so here's a sort of representation of what's going on. You start off with initial state here, the system rotates, and at a particular time, all the particles, as you're going from time 0 up to tau here, particles move around, but then they all come together at time tau in site 2. And then you go from time tau to 2 tau, then they move around and they all come together at site 3 and then back to site 1. Okay, so the expression I had here before for the xi, that basically is telling us what the period is for this rotation. And what we see here is, it's interesting, is that the period of the rotation for this process depends on N4. So that's the number of particles at site 4, which is at the top of the tetrahedron. So this acts as a control. You can control the frequency of the tunneling independent of the rotation of the actual physical device by changing the particle numbers at site 4. And basically the particle number at site 4 just remains constant through the dynamics. It doesn't change. Now this is not 100% accurate, not 100% accurate. So it's not as if the state is exactly all the particles being transferred like from site 1 to site 2. There's a very small probability that you might observe particles at site 2 and 3, but it's tiny. So to quantify the accuracy of what's going on here, we use what's called the fidelity, which is just measuring the overlap. So if you take this system and compute the evolution of the state at this time, and then take the overlap between that state and the actual Fock state at that time, that's what we call the fidelity. So it's a number that lies between 0 and 1. And so here are our computations for those fidelity expressions. So this first case here, that's one I just showed you with the Fock state. So you can see here, this is 0.99. So it's not 100% accurate, this process, but it's very high fidelity. It's almost a 1. Very small probability that you'd measure particles at site 2 and 3 at time tau. These calculations here are showing both numerical calculations from direct diagonalization of the Hamiltonian and expressions that we got from the beta ansatz calculations, which are too technical for me to describe. But basically, you can see in this second one here that the beta ansatz calculation sort of gives you the average, and the actual simulations oscillate about those averages. Here, the oscillation amplitude is so small you can barely see it. You can see it in the second and third cases. So the first one is for a Fock state. Second one's for an entangled state called a noon state. And then the third one is what we call an uber noon state. And I've got just enough time to say something about those. So if we take a entangled state of this form, this is called a noon state. So it's a superposition of n particles at one site and none at another site, superimposed with the reverse, 0 and n. So for a noon state, we can apply this in two ways. We can start with a noon state across sites 1 and 4 and look at the evolution. or we can put a noon state across sites 1 and 2, so have an entangled state across these sites. And basically, because the evolution in a quantum system is unitary, then it works for entangled states just as well as it does for non-entangled states. So here we find that we get something very similar, that this entangled state rotates around the quantum term table in this manner, and this entangled state here does so in this sort of fashion. Then we can do what's known as an Ubernoon state. And so an Ubernoon state is like an entangled state of noon states. So this is a noon state here with a plus phase, and this is a noon state here with a negative phase, and then you take a superposition of those noon states with these states here. So these are states, these are four-site states. We're using all four sites in the turntable. And if we start off with this as the initial state and then let the system evolve, then we find at this particular time tau that this state here evolves to this state here, and it picks up this phase. So not only does it rotate, does this four-site entangled state rotate around the system, but it rotates with this phase appearing in the evolution, and that phase is given by this. And this phase here, I haven't got time to talk about it now, but this phase is really what's quite interesting in using this turntable as a kind of sensing device. The fact that it can pick up these phases can be used. So basically, people use quantum systems to do things like sensing of gravitational waves or whatever, appealing to systems that pick up phases in the evolution, and then you measure those phases through some sort of process. Okay, so I'm going to finish up there. So just some references. This work that I've talked about today has been published quite recently in this journal called Newton. It's a new journal that's just started publishing this year. And that's built on some earlier works with my colleagues, including Lachlan, who is a PhD student who finished up this year, and Phil Isaac here at UQ, and Angela, who leads the group in Brazil that collaborates with us. So all of these other people here over in Brazil with Angela. This paper here talks about these sort of superintegrability properties of these constructions. So what I showed today is just one example of how you can build these superintegrable bosonic systems. And we have some earlier work on the sort of noon state protocols, which are relevant to what I've described today. And I also want to finally just give a shout out to Owen, who will be giving a talk this afternoon on closely related topics. He's been undertaking a project with me and Sam Colt this year, and he'll be talking about similar things. So I'll leave it there, and thank you. And are there any questions?
Thank you very much, Jon. So I did have a question actually, where you mentioned that the individual dipoles had an electrostatic interaction, but where was this present in the bosonic model?
Oh, I should have said, so what you do is you put the whole system in a field. So if you were to so we talked about this in the paper. So there's particular types of atoms. There's dysprosium, erbium, for example, which naturally have such naturally occurring dipole moments, and you just basically put them in a field to align them, so they're all lined up in that vertical direction. And then,
But
then
like the bosonic like so these are atoms that are moving from the individual dipole.
yeah. So this is so the way you would implement this would be through some cold atom system. So you have something at nanokelvin temperatures, and so you have individual atoms that are moving around on this tetrahedron. So it's quite complicated. You have to set up these system of lasers to trap the particles at these four sites, and and then rotate it, and then they can tunnel between the sites. But you have it in a magnetic field, which forces all of the dipoles to align in the vertical direction there. And then you get the different interactions between those sites in the bottom plane here, compared with the ones interacting with the site labeled 4.
Alrighty, let's just give another thank you to John for the excellent talk today. Um, I believe we have next CU, who's going to um, discuss the stack